This is MAT 221. This is section 3.3 talking about the trigonometric rules for derivatives. This is an example when we're talking about oscillating motion or motion of a spring. So for instance, if you had an object at the end of a vertical spring and it's being stretched 4 centimeters beyond its rest position and then released at time equals 0, the spring will bounce up and down. So if you look at the figure that's here. So its position at any given time t is given by this trigonometric function. The position is f of t, which is 4 cosine of t. And if I was asked to find the velocity and the acceleration at any time t, and then use them to analyze the motion of the object, remember we would simply use what we know about what acceleration and velocity are compared to a position function. So a position function, remember, the first derivative would be the velocity. So if I took the first derivative of this function, that would give me the velocity of the object. And if I took the second derivative, or the derivative of the velocity, that would give me the acceleration of this object. So given the curve here, the first derivative would be the derivative of 4 cosine of t, which is a pretty easy derivative now using our new rule, which would be 4 cosine derivative of cosine of t, which is negative 4 sine of t. And then the derivative of that would be the second derivative of position, which is acceleration, would be negative 4 times the derivative of sine, which we know the derivative of sine is just cosine. So we have the position function was equal to 4 cosine of t. The velocity function is now negative 4 sine of t, and the acceleration function is negative 4 cosine of t. Now I want you to notice, as opposed to other functions that when we use polynomials, the trig functions are cyclical because of their periodic nature, and they'll never end up going to 0. They'll always, again, be very cyclical here. So what do I know? I know that the object oscillates from its lowest point at s equals 4 centimeters, that's when it began at time equals 0, to its highest point of negative 4 centimeters. And the period of the oscillation is 2 pi because the period of cosine is 2 pi. So remember, speed is equal to the absolute value of velocity. So if I took the absolute value of the velocity, I would get the speed at when time equals 0 is equal to 0. So the object moves fastest when it passes through the equilibrium position at s equals 0 with a speed of 0, and then the sine of t when the sine of t is equal to 0. If I graph these three functions, that would help us the most. When we look, the acceleration is negative 4 cosine of t. It'll equal 0 when s equals 0, and it will have the greatest magnitude at those high and low points, as you notice. So here's my position function. Starts out at time equals 0 is equal to 4, and then drops to negative 4, and then we'll come back up to positive 4 again. Here's my velocity at time equals 0 was 0, and then the velocity was negative, going in the negative direction, right? Highest here, and then came back to 0 at pi, and then highest here, and then came back to 0 at 2 pi. And here's my acceleration function. My acceleration was negative, then positive, then negative again. All right, so that ends our section for section 3.3 on trigonometric functions. There are several worksheets in the worksheet folder on both the product and quotient rule and on trigonometric functions that you could practice if you'd like to practice more skills on working with the 6 trigonometric functions and their derivatives. Have a good day.